Hello. In this video, I'm going to go over section 11.5, the chain rule. Now, the reason why we're looking at the chain rule in Calculus 3, it's because when we were using the chain rule to solve related rates problems in Calculus 1, say for example for the cone, we had to make sure to have a relationship between the height and the radius because of the formula for volume. The formula of the volume of a cone, it's 1/3 pi r squared h, and we didn't know how to compute the derivative if my function v was a function of two variables r and h, where both were functions of t. Okay, so now we will be able to compute those without having to turn the volume formula function into a function of one and only one variable. Okay, so let me remind you of how this works in calculus 1. If I have that y is equal to cosine of t to the fifth, and I want to find the derivative with respect to t, then I can think of cosine of t as x of t and apply the chain rule, right? So just to remind you, if I have f of g of x, I want to find the derivative of f of g of x. I take the derivative of the outer, replace with the inner function, and then come back and multiply by the derivative of the inner function. Okay. Well, so that means if I use now Leibniz notation, dy dt, it's equal to, take the 5, bring it to the front. So this is 5. I'm going to leave my x of t alone, and this is to the fourth, multiplied by the derivative of the inner function, which is just dx dt. Now, if you think about it, this right here, it's just equal to the derivative of y with respect to x, and then multiply by the derivative of x with respect to t. Okay, so this is another way of writing the chain rule. Now, what we're going to use to remember this formula is something called a tree, and that tree of derivatives will tell you how to put together the chain rule now in higher dimensions. So let's start easy with this case. So if I have, let me just say tree of derivatives. So if I have y as a function of x and x is a function of t, and I want to find the derivative of y with respect to t, I want dy dt, you have to go through x first. This would be dy dx and then dx dt. And see how I'm using d and not the partial, because y depends on x and x depends on t. Okay, in my first example, the first definition, which is the case where z depends on x and y, and then both of them depend on t, it's going to be a little different. So let me start with z. It's a function of x and x is a function of t, but then z is also a function of y and y is a function of t. So we're going to do exactly what we did before. I want to get to dz dt. I'm going to need to find all these derivatives and then add them together. Okay, so it's like I have two branches. The way we do this is we go, okay, z is a function of x and y. So if I take the derivative of z with respect to x, that it's going to be a partial derivative. So this is partial of z with respect to x. But then x only depends on t, so this is a complete one dx dt. Same thing happens on the right hand side. I have dz dy and then dy dt for the same reason. Okay, now x and y here, let me maybe use pink for this. X and y here, these are called intermediate variables. So intermediate variables, and then t, it's my independent variable. Okay, independent variable. And then I put together my derivative and I get that dz dt, which I'm not using partials because then it's just the final one, right? There's only one independent variable. Since there's only one independent variable, this is a complete derivative. I'm going to get that this is dz dx partial times dx dt, and then I do it for when I go through the other branch. Okay, so I get that this is dz dy dy dt. Now, we're not going to prove these things. It's just an extension of the chain rule. and the tree only helps you remember the formula, okay? And we're going to see that you can have a bunch of different intermediate variables that depend on a bunch of independent variables. So it's good to know how to use this tree. Let's do an example. So we're going to find dz dt if z is defined as x squared plus y squared plus x times y, and x is equal to sine of t and y is equal to 3e to the t power, okay? So again, we have two intermediate variables and one independent variable t. So we will be using this tree, which is just this definition of the derivative. I'm going to do it two different ways. I'm going to do it directly first, directly, so that you see how we would do this in calculus 1. And then I'll do it using the chain rule in higher dimensions so that you see that we get the same answer. Okay, this is easy enough that we can do it like that. So now let me start by rewriting this. So z is equal to x squared, but x is equal to sine t. So I get sine square of t plus y squared, but y is equal to 3et. So if I square, I get 9e to the 2t. And then I have to multiply x and y, so I get sine of t times 3e to the t power, okay? Now, if I compute the derivative with respect to t, I have to use the chain rule here, so I get 2 times sine of t times the derivative of sine, which is cosine of t, plus the derivative of 9e to the 2t. I have to use the chain rule. I get 9e to the 2t times the derivative of the exponent, which is 2. And then for the derivative of sine of t, 3e to the t, I have to use the product rule. So I would get that this is equal to, I'm going to do second one, 3e to the t, times the derivative of the first one, cosine of t, plus the first one, sine of t, times the derivative of the second one, which is just 3e to the t. Okay, so that's what I got. Now, I could simplify this. Let me see. I could simplify this, but I'll wait until I do it using the chain rule to see which one is more convenient. Now, if I'm using the chain rule, I know that dz dt, it's equal to partial z with respect to x, and then dx dt, and then plus partial z with respect to y, and then dy dt. So let's see. If I take the derivative of the partial of z with respect to x, I take the derivative of this with respect to x, so I treat y as a constant. So dz dx, it's equal to, well, 2x plus y. If I take the derivative with respect to y, I get dz dy. Now I treat x like a constant, so I get 2y plus, so this goes away, and then 2y, and then the derivative of xy will be just x. So this is 2y plus x. And now I take the derivatives of x and y with respect to t. So dx dt, it's equal to cosine of t, and dy dt, it's equal to 3e to the t. And then I'm ready to put together this derivative. So I get that dz dt, it's equal to, well, dz dx, I get 2x plus y times dx dt. So I get times cosine of t plus dz dy, it's equal to 2y plus x, and then dy dt, it's 3e to the t power. Okay, so one more time, let me color code this a little bit. So dz dx is 2x plus y, which is right here. And then I get dx dt, it's equal to cosine of t, which is right here. And then I get dz dy, it's equal to 2y plus x, which is right here. And then finally I get the dy dt, it's equal to 3et, which is right here. And then you can stop here. Stop here. This is going to be your derivative. There's no need to go back and replace x and y with sine t and 3e to the t, because we know what they are. But just so that you see that we actually get the correct answer, I'm going to go ahead and replace x and y with the definitions. So this is just to see that it works. I get 2 times, and then x is sine of t plus 3e to the t times cosine of t. And then I get plus 2 times, and y is equal to 2 times 3e to the t plus x, which is sine of t, and then the whole thing multiplied by 3e to the t, okay? So if you compare this to this, you get exactly the same thing, right? So this is 2 sine t cosine, 2 sine t cosine. And then here I get 2 times 3, you get 6. You get, wait, I'm here. 3 times 3e to the t cosine of t. So 3e to the t cosine of t is right here. And then here I get that this is 2 times 2 times 3t, that's 6e to the t times 3e to the t, you get 18. And then, which is right here, so 9 times 2, you get 18e to the 2t. And then finally 3et sine t, which is right here, okay? So you get exactly the same thing, but you can just leave it like this. All right. All right, so this is a nice example because we have to find dz dt, where z is a function of x and x and y are functions of t, but we don't know what they are actually are, so we have to use the chain rule. So then we know that dz dt, it's equal to the partial of z with respect to x, and then dx dt, plus the partial of z with respect to y, and then dy dt. Now, z is just f, so if I'm looking for the partial of z respect to x, this is just the partial of f respect to x. So this would be the partial, and this is going to be at x of t, y of t, and then dx dt is just x prime of t plus the partial of with respect to y, x of t, y of t, and then we have that dy dt is just y prime of t. Now, one more intermediate step. I know that x is actually g of t, so this would be the partial respect to x, and then g of t, h of t times, and x prime will be just g prime, so this is g prime of t plus the partial respect to y, and then again we have g of t, y of t, and then g of t, h of t, h of t, and then y prime of t is just h prime of t. Well, that means that if I'm looking for dz dt evaluated at t equals 1, this is just equal to fx, and then g of 1, well, g of 1 is equal to -3, so this is -3. h of 1 is equal to 1, and then g prime of 1 is equal to 3, plus, and then I have my partial with respect to y evaluated at -3, 1, and h prime of 1 is equal to 5. So one more step, and I get that this is 9 times 3. So one more time, here we have partial respect to x, it's equal to 9, and then plus the partial with respect to y, it's equal to 8. So I get here 8 times 5. So this is 9 times 3, you get 27, plus 5 times 8, which is 40. Final answer, we get 67. Okay. Now we have another nice example, which is a related rates problem, very similar to what I was talking about at the beginning of this video. So now we have that the radius of a right circular cone is increasing at a rate of 1.3 inches per second. So if the radius is increasing, then that tells me that this is going to be my dr dt. So the radius, so that means that this is dr dt. And then it says while the height is decreasing at a rate of, so since it is decreasing, it'll be negative. So we have that dh dt, it's equal to -2.8, right? It'll be negative. At what rate is the volume of the cone changing? So we're looking for dv dt exactly when the radius is equal to 135 inches and the height is 185 inches. So one more time, there's no need to write one variable in terms of the other one, because now we know how to find the derivative of a function in two variables. Okay, so let's see. Step 1, we're going to read the problem. It's done, we read it. Step 2, we need some variables, maybe a diagram if it helps. Okay, so let's see, what do we have? The radius of a right circular cone is increasing at a rate. So dr dt, it's equal to 1.3 inches per second. And then we keep going, and it says, and the height is decreasing, so dh dt, it's equal to negative 2.8 inches per second. At what rate is the volume? So we're looking for dv dt exactly when, so exactly when the radius is equal to 135 inches and the height is equal to 185 inches, okay? Step 3, I need a formula relating the quantities. And my formula is, well, the volume of a cone, which we know it's 1/3 pi r squared h. My next step is to take the derivative to relate the rate. So we want to take the derivative with respect to t. So let's review what we have. We have that volume, it's a function of both radius and height, and then the radius changes only with respect to t, and the height changes with respect to t too. Okay. Now, since volume it's a function in two variables, to take the derivative of v respect to r, this is going to be a partial derivative. Same reasoning behind having a partial derivative here, but then to go from r to t, it's only one variable, so this is a complete one, okay? So what I'm saying is that dv dt, it's equal to the partial of v with respect to r, and then the derivative of r with respect to t, plus the partial of v with respect to h, and then the derivative of h with respect to t, okay? So let's see, what else do we need? Well, dv dr, I have to take the partial. I need the partial of v with respect to r. So this is v. If I take the derivative with respect to r, h is constant. So I get that this is 2/3 pi r h. And then I take the derivative of v with respect to h now. Now r, it's treated as a constant. So I get 1/3 pi r squared. So 1/3 pi r squared, and the rest we know from the little story here, okay? So my next step, I'm ready to answer the question. So step 5, answer the question. Answer the question. And the question is, how is the volume changing? Well, dv dt, it's equal to dv dr, exactly when r is equal to 135 and h is equal to 185. So I get that dv dr is equal to 2/3 pi, r is equal to 135, and h is equal to 185. And then I get dr dt. Well, dr dt according to this is equal to 1.3. And then I get plus dvdh. So dvdh, when r is equal to 135, that gives you 1/3 pi, and then 135 squared dh dt, which is negative 2.8. So let me make it blue. So negative 2.8, okay? Now we use a calculator, put everything in the calculator, and we get that this is equal to, let's see, I get that this is equal to 4,635 inches cubed per second, right? Because we're dealing with volume, so we need cubed, okay? Perfect. Now, imagine you have a function z that actually depends on two variables, and then those two variables, right? Those two variables depend on two variables. So, long story short, this s and t, these are my independent variables, and x and y are my intermediate variables. So, let's see. Let's see, what do we have? So we have z, and then z depends on x and y, but then x depends on s and t, and y depends on s and t, okay? So if I'm trying to get to dz ds, for example, I have to do the same thing we did before, and I have to find a way of getting to s using all the branches. So let's see. So this will be, I'm going to go dz, dx, dx, ds, right? And then again, z is a function of two variables, so this is partial. X is a function of two variables, is also partial. And then I still have to add if I go through y instead, okay? So dz, dy, partial, and then I get 2s, okay? So then this is going to be equal to, so my partial here. So it's going to be equal to partial of z with respect to x times the partial of x with respect to s plus partial of z with respect to y times the partial of y with respect to s. And if I have to do it for t, it's exactly the same thing, okay? If I have to do it for t, then I have to go through the branches. So I'll do dz, dx, dx, dt, or d, and then plus dz, dy, dy, dt. Okay, so this would be dz, dy, dy, dt. And I don't know why I did y first, but it's all the same. And this is dz, dx, dx, dt plus dz, dy, dt. Okay, perfect. That's an example. I want to find dz, ds, and dz, dt for z defined as x cubed, y cubed, and x is equal to s times cosine t, and y is equal to s times sine t, okay? So let's do dz ds first. So dz ds, again, it's equal to dz dx dx ds plus dz dy dy ds, okay? So what do we need? Let's see. Dz dx, I go to here and I treat y like a constant, so I get that this is equal to 3x squared y cubed, okay? Then dx ds, it's equal to dx ds, it's equal to, I go to here and I treat t as a constant, so I get that this is just the derivative of x respect to s is equal to cosine of t. Then I get that dz dy, well, I go to here and I treat x as a constant, so I get 3x cubed y squared. And then finally I have dy ds, that's equal to, go to here, I treat t as a constant, so I get that this is just sine of t. So I'm ready to put together my derivative. So this is going to be equal to dz dx equal to 3x squared y cubed, so 3x squared y cubed times dx dx ds, which is cosine of t, plus dz dy, which is 3x cubed y squared, so 3x cubed y squared, and then dy ds, it's equal to sine of t. Perfect. Now to find the partial of z with respect to t, I'm going to do exactly the same thing, but now with respect to t. So I get dz dx dx dt plus dz dy dy dt. The beauty of this is that this dz dx is the same as this dz dx, which is the same as this partial of z with respect to x. And same thing happens here for the dz dy is the same as dz dy is the same as dz dy. So to get to this derivative, I only have to find dx dt and dy dt, the partials, right? So if I do dx dt, I get that now I'm going to treat s as a constant. So I get that this is negative s sine of t, right? And dy dt, I treat s as a constant, so I get s cosine of t, and then replace everything with the derivative we just computed, and we get 3x squared y cubed times dx dt, which is negative s times sine t. So negative s times sine of t plus dz dy, which is 3x cubed y squared times dy dt, which is s times cosine of t. Okay? Perfection. All right. Hope that makes sense. What else do we have? Now, this is what I was saying at the beginning of my video. What if I have, in this case, there are m independent variables, and 1, 2, all the way to n intermediate variables. Okay, so one more time. These are my independent variables. So I have m independent variables, and I have n intermediate variables. Okay, so we make little tree to understand what's happening. So long story short, I have here, I start with z, but z has n intermediate variables. So I have x1, x2, dot dot dot, xn. And each of these x's have m independent variables. So this would be t1, t2, dot dot dot, tm, and then x2 has m, and then xn has m, and so on. So if I want to find dz dti, right, I'm gonna go here. I'm going to assume that this is my ith now. So I would have to do dz dx1 dx1 dti, and then dz dx2, and then dx2 dti, and so on. Okay, and so on. So this would be equal to, let's see, it'll be dz dx1, and then dx1 dti, plus dz dx2 dx2 dti, plus, and so on, dot dot dot, plus dz dxn dxn dti. And then I'm going to have the same thing for all m of them. Okay, so let's do an example. Here we want to find dwdr and dwd theta evaluated at r equals to theta equals to pi over 2, where w is equal to xy plus yz plus zx, and x is equal to r cosine theta, y is equal to r sine theta, and z is equal to r theta. So let's see, what do we have here? We have w, and w is a function of x, y, and z. So x, y, and z, x, y, and z, and then x is a function of r and theta, y is a function of r and theta, and z is a function of r and theta. Okay, so that means that to get from one variable to the next one, right, we're going to use partials, because w is a function in three variables and x is a function of two variables. Okay, so let's find dwdr first. So dwdr, I have to get to r through all the possible branches. Okay, so it'll be dw dx dx dr plus dw dy dy dr plus dw dz dz dr. So this is equal to the partial of w with respect to x. So partial of w with respect to x, and the partial of x with respect to r, plus the partial of w with respect to y, and the partial of y with respect to r, and then plus the partial of w with respect to z, and then the partial of z with respect to r, and we're done with my dw dr. Okay, now dw dx, it's equal to, well, dw dx, the partial of w with respect to x, is equal to, go to here and treat y and z as constants. Okay, so I get that this is equal to y plus, and then here I get, with respect to x, I get y, this goes away, and I get plus z, and then dx dr, well, dx dr, it's equal to, I go to here and I treat theta as a constant, so I get that this is cosine theta. And then dw dy, it's equal to, I treat now x and z as constants, so I get here that this is x, and then the derivative with respect to y here will be z, and then this goes away, and I take dy dr, so I go here, and now I treat theta as a constant, so I get that this is sine theta, and finally I do dw dz, go to the definition of w, and treat x and y as constants. So this goes away and I get y plus, and then zx with respect to z, I'm going to get that this is x. This is x, and then dz dr, it's equal to, treat theta as a constant, and I get that this is just theta. Okay, perfect. Now I need to evaluate everything at 2 and pi, and r equals 2 and theta equals pi over 2. So let me just do it real quick for x, y, and z. So x is equal to 2 cosine of pi over 2, which is equal to 2 times 0. So I get 0. y it's equal to y it's equal to 2 times sine of pi over 2, which is equal to 2 times 1. So I get 2. And finally, z it's equal to r times theta. So 2 times pi over 2, I get pi. Okay. So that means that dw for this case, right? dw dx is just equal to y plus z. So I get 2 plus pi, and then x plus z, I get that is just pi, and then y plus x is equal to y plus x is equal to 2. And then if I do the same thing, I get that dx dr is cosine of pi over 2, which is equal to 0. And then dy dr is equal to sine of pi over 2, which is equal to 1. And then finally dz dr is equal to theta, which is it's equal to pi over 2. So I'm ready to find this derivative. So putting all together, we get that dw dr evaluated at r equals 2 and theta equals pi over 2. It's equal to, well, dw dx, which is equal to 2 plus pi, 2 plus pi, and then times dx dr, which is 0, so that goes away, plus, and then dw dy, which is pi times, and then we have dy dr, which is equal to 1, so I get 1 plus, and then dw dz, well, dw dz, it's equal to 2 times dz dr, which is just pi over 2. And if I simplify this thing, I'm going to get that this is, well, 0 plus pi, which is equal to 2 pi. Okay. Now, dw d theta at r equals 2, theta equals pi over 2, you do it. You should get negative 2 pi. You do it, okay? All right, I hope everything made sense. Bye-bye.